We are the Society for Advanced Rocket Propulsion, otherwise known as SARP, a student-led organization at the University of Washington that designs, builds, tests, and launches a rocket for competition each year. As a team, we've been pushing the boundaries of collegiate rocketry since 2012, and we are aiming to reach the edge of space with a rocket by 2025. When reaching for space, every ounce counts. More mass means more that the Earth's gravity holds our rocket back. To this extent, given our current propulsion system, every pound of weight that we shave off yields us 100 feet of higher apogee. One way to cut back on weight is to use materials with high strength to weight ratios, such as carbon fiber.
Our Capstone team pursued an R&D carbon fiber coupler, and we are planning to have a similar part replace the weighty all-aluminum design that SARP has used for the past 6 years. This part, known as the recovery coupler, serves as the hard point during parachute deployment and has to withstand the shock loads delivered by the parachutes, as well as the thrust and acceleration generated by launch of the rocket engine. By switching the material to a carbon fiber, we utilize the material's strengths, keep the original functionality of the recovery coupler, save weight, and thus increase apogee. This design was optimized using analysis ran in ANSYS ACP, a composite analysis software that reassures the practicality and safety of the design. The carbon coupler weighs 48% of the aluminum alternative and will give the rocket an additional 240 feet in altitude.
This coupler is also enhancing SARP's baseline of composite manufacturing skills. The coupler needed a new mandrel, an aluminum mold that plies of carbon fiber were placed over to create the part. The mandrel was manufactured in-house by the team in a precision machine shop and consists of two pieces, a tube and bulkhead that bolt together. The mandrel was treated with chemicals to seal the surface and prevent the coupler from sticking to it, giving the coupler a superior surface finish. Our manufacturing process has been optimized through multiple practice layups that proved the repeatability and reliability of the process. To manufacture the coupler, the mandrel was rolled over carbon plies and then folded over the top, in a pattern that enhances the strength and reduces the safety risks normally associated with carbon fiber.
The coupler is currently in post-processing and will go through testing by the end of the development period. These tests will ensure that it withstands the associated loads in real life, not just in simulations, and repeated loading will demonstrate the reliability of the design. The part is not only impressive in the context of student-developed rocketry, the geometry is complex, so our design and associated processes are substantial even in the realm of aerospace. Composites like carbon fiber and fiberglass are being utilized more and more in aerospace as well, because reducing the weight of the rocket means that it requires less fuel to reach the same altitude. This is not only more cost-effective, but also reduces the carbon footprint per launch, which is substantial in commercial aerospace. This coupler is a giant leap forward for SARP and will give the team more flexibility as it pushes onwards towards space.
Do it.